So this is number 22 in chapter 8, and it has to do with aromaticity, anti-aromaticity, and non-aromatic compounds. So there's a couple different ones. One we showed in class is this one. All right, so essentially the first thing you need to know the qualifications to be aromatic. So there's two things you need to be aromatic. The first one is what? Uninterrupted pi system, not just pi bonds, pi system in a ring, right? Has to be in a ring. Uninterrupted pi system, right? That means you can have lone pairs, that means you can have pi bonds, right? Uninterrupted pi system in a ring. The other rule? Odd number of electron pairs in the pi system, right? And this is for aromatic, right? That's aromatic. If you want to do anti-aromatic, what was the switch? Even number of pairs of electrons. That's the anti-aromaticity one. Non-aromatic, right? Essentially, right? Not in a ring, right? Not uninterrupted. Most things, right, are non-aromatic. All right. So let's look at this one right here, though. So does this have an uninterrupted pi system in a ring? Yes, it does, right? The way you look at it is, does it have any sp3 hybridized elements in there? No, right? sp2, and then this, right, is choosing to be sp2 so it can be part of the pi system. Right, so this one's kind of a tricky one. You could even say, right, so how many pairs of electrons are in the pi system here? Two. So what is this? Aromatic, non-aromatic, or anti-aromatic? Anti-aromatic, that's right. It's anti. Good.
So the lone pair can't be in a pi orbital?
It's in a p orbital. There's no such thing as a pi orbital. Right, p orbital. It is in a p orbital. That's the next question I'd ask you is, what's the hybridization state of that carbon? sp2. And so what orbital are these lone pairs located in? Right.
So that means this.
Another one they had. This one. Right? So now be careful, right? When we make tests, we make quizzes, we don't draw on the lone pairs. Right? And sampling a lot of times asks you to do that too. So you should start doing that yourself, right? Drawing in the lone pairs. Seeing a nitrogen with 3 bonds and saying, oh wait, a nitrogen also has a lone pair. So let's draw that in. But we might not give that to you. That doesn't mean, right, it's not there. Also, does it matter where I draw? If I drew the lone pairs here or if I drew them over here, does it matter? No, right? It's just a matter of, right? I could draw these lone pairs on this side, not be in the ring, but that doesn't mean they're not still part of the pi system, right? It looks nicer when they're in the ring, right? But so first question: is this an uninterrupted pi system? Right? sp2, 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 sp2. Okay. How many pairs of electrons are there? 1, 2, 3, 4, 5. Right?
Are we
Right. The pairs, yep. There's 5 pairs. Right, so what kind of compound is this? Aromatic, anti-aromatic, or non-aromatic? So this one is actually non-aromatic.
Is that because it's not flat or
Nope. The reason it's non-aromatic is, right, so to be aromatic, when we say an uninterrupted pi system, what are we talking about? Right? Everything has to be flat, right? So it's all flat. So if you look at this molecule, right, there's positions right here where things probably don't want to be flat, right? There's H's here. There's an H here, right? That are probably getting in the way, and so the ring will actually pucker. It won't stay flat. And if it doesn't stay flat, it can't be an uninterrupted pi system.
On the test, though, you are going to say assume.
Right. This is like, this gets back to this could be a good extra credit kind of question where we give you this kind of problem and say, interpret these are the results, interpret these results. What does that mean? right? So, but in reality, this is non-aromatic, right? Because it has to be an uninterrupted pi system, right? And the other way to think about this, right? Even if you don't realize it's not uninterrupted, if I told you this compound was non-aromatic, right? I told you it's non-aromatic, and I ask you for why. Well, can you change the fact that there's 5 pairs of electrons in that thing? That can never change. So what could change? How the molecule's conformation is, right? So that's what's the only thing that could change. So it could say, the reason it's not aromatic is because it's puckered. Because the molecules move so the pi system isn't uninterrupted anymore. It's made that choice. Okay, so I just made up this molecule. It probably doesn't really exist, but I just made it up. But again, let's ask ourselves the questions for aromaticity. Let's figure out if it's aromatic, non-aromatic, or anti-aromatic. First thing I would do, if they're not given, draw in the lone pairs. Right? Draw in the lone pairs. So in this case, does nitrogen have a lone pair? Yes, it does. Does sulfur have missing a lone pair? Yes, it is missing a lone pair. Sulfur has, right? Sulfur's right below oxygen. Oxygen normally wants 2 bonds and it has 2 lone pairs. If sulfur, just like oxygen, has an extra bond, it still has a lone pair. Still has a lone pair. Just because they're lone pairs doesn't mean, right? We got to think about what orbitals they belong in then too. All right, so let's ask ourselves that question right now. What's the hybridization state of that nitrogen? Hybrid state. It's sp2. What molecular orbital is that lone pair in? sp2, right? Is this lone pair part of the pi system? No, it's in an sp2 orbital, right? It's perpendicular. It's 90 degrees away. What about this sulfur? What's the hybrid state of that sulfur? It's sp2, right? It has a pi bond. It has 1 pi bond. It's sp2. That lone pair, what molecular orbital is that lone pair in? Is that lone pair part of the pi system? No. This carbon right here, part of the alkyne. What hybrid state is it? sp. Are both of these pi bonds in the pi system? No. So don't forget, right? A triple bond, what it looks like. Right? There's 1 p orbital, and then there's a second one. Right? And what is the bond angle from here to here? 90. All right, so one of these pi bonds is part of the pi system, but the other one is not. I don't know which one, but right, one of them is part of the pi system, but the other one is not. Right? Just like these lone pairs are not part of the pi system, one of these pi bonds is not part of the pi system. Cool? So is it an uninterrupted pi system at this point? 1, 2, 3, 4, 5. Yep, looks like they're all sp2. Right? Is there an odd number of pairs of electrons in the pi system? 1, 2, 3, 4, and 5. So I would call this aromatic. All right, so that makes sense about the, right? Notice how we've been saying all along, an uninterrupted pi system in the ring, it really means no sp3. I didn't say no sp, right? You can have sp and sp2 hybridized things in these rings. Right? For sure not sp3. Because sp3 has no p orbitals. Right? An uninterrupted pi system means everybody has at least a p orbital.
So in this case, we are counting the lone pairs?
Not as part of the pi system. Right? These lone pairs are not part of the pi system.
So you said there's 1 in a P and 1 in a, or sorry, 2 in a P and 2 in an, hold on, 2 in a P and 2 in an SP.
No. These lone pairs are in
No.
sp2 orbital.
No, I'm talking about, yeah, there.
sp. They're both sp hybridized.
Okay.
But only one of the pi bonds between those 2 carbons is part of the pi system. Right? Because the other one's 90 degrees away.
I see what you're saying.
And these lone pairs, right, aren't in p orbitals, so they can't be part of the pi system. That's in an sp2 orbital. That's in an sp2 orbital. Just because there's a lone pair doesn't mean it's in a p orbital, right? And sometimes, right, if I drew something like this, right, one lone pair can be in a p orbital and the other one cannot be, right? Okay, so this is, I think it's number 35 in chapter 7, practice. But it involves an alkyne, an internal alkyne, remember? And it's a symmetrical internal alkyne, which really matters, right? This, if we numbered our carbons, 1, 2, 3, 4, 5, and 6, how many carbon 13 signals would we expect out of this molecule? How many C13 peaks would we see? 3, right? That's one of the reasons why we did that NMR first, right? Is to make you guys start recognizing symmetry in molecules, right? So that's important, right? Because if carbon 3 and 4 were different, we could actually get 2 different products here, right? So let's see. We're going to react this with, it's going to be Hg 2 plus, H plus is floating around, and water.
Oh, and I remember what my question.
Okay, so the first step, we got to identify electrophile and nucleophile. So what's my nucleophile? Pi bond. My electrophile then is mercury, right? Some people might say, why not H plus? Well, mercury is 2 plus, so that's more plus. I don't know. You could do it either way, actually, but the mercury is probably what gets attacked. So this is 2 arrows, right? Because there's nothing attached to the mercury, right? So we make our mercurium ion, put the plus charge there. Now we still have H plus floating around. We have water floating around. So H plus is an electrophile, right? And what is this mercurium ion going to be? Electrophile or nucleophile, do you think? Is this an electrophile? Is this electron rich or electron poor? It's electron poor, right? You got to know this, guys. Right, it has to be electron poor. So I'm not going to react it with this, I'm going to react it with this, the water, which has electron density in the lone pairs. Now if I number my carbons again, does it matter if I attack carbon 3 or carbon 4? No, because carbon 3 and 4 are the same, right? Balance our charge. The biggest thing that's really important here is to show, right, that the water that added and the mercury that's still on there, they're trans to each other. You have to show that they're trans to each other, right? It's a trans addition, right? Now at this point, what do we want to do? The whole point of this, the other point of this is to get the mercury off of there, right? So you need to figure out ways to get the mercury off there. The first thing we can do, there's a couple of ways you can do this. I would do this tautomerization step, where carbon 4 gets the H, right? Oh, excuse me, I'm going to draw this a little different. These electrons are going to go between the oxygen and 3 and make that pi bond right away. Okay. So now at this point, right, oxygen has a plus charge. Oxygen doesn't want a plus charge, right? We want to keep trying to give electrons to oxygen. So the mercury is going to, mercury carbon bond. The carbon actually has the electron density, so the mercury is just going to leave. All right, number my carbons, 1, 2, 3, 4, 5, 6. And as that happens, electrons go to the oxygen. The pi bond between 3 and O breaks as we form a new pi bond between 4 and 3. And we also, right, made mercury plus again. So we lost mercury there. Now at this point, we still haven't used, right? What have you not used? You haven't used the H plus at all yet, right? So let's use the H plus. Right, so what is this called right here? This is called a enol, and so this is usually the minor product, right? Usually the ketones and aldehydes don't exist as enols, they usually turn themselves back into carbonyls, right? So this is an enol, and it's going to react with H plus. So I put the H plus in here. This pi bond is going to go for that. 1, 2, 3, 4, 5, 6. Right? And where would we rather put the, if we had to put a plus charge somewhere, where do you think the H is going to go? On carbon 3 or carbon 4? Going on 4, right? And at the same time, these electrons between that O and the H, again, are going to go between oxygen and carbon 3. And so what I did there, right, this bond broke and I also regenerated H plus, right? Everybody see how I did that? All of a sudden, right, this hydrogen lost 2 electrons, so I've remade H plus at the same time. I could have done it stepwise too. Plus H plus. And this H is this H. 1, 2, 3, 4, 5, 6.
Electrons in the pi bond are going to the H.
Yep.
How, just to regenerate H? Or-
Wait, so to regenerate, to turn this enol into a ketone.
Could you also have had like the water, the lone pairs on oxygen attack? I mean, it would still generate H3O plus.
Yeah, you could use water instead of right. H3O plus is the same as H plus. H2SO4 is the same as H plus and H3O plus. It's all the same. Yeah, you could use the water to do this too, if you wanted to have like water take this. But then H3O plus is the same as H plus. Yep.
Are there any uses for this in reducing mercury?
So actually, I don't know if it does exactly reduce mercury.
Okay,
I think it still stays the same. We asked you guys not to worry about the oxidation state, so don't worry about the oxidation state.
Alright.
The biggest thing is you don't want mercury on carbon. So if you can remember that, when you get stuck at this point, you're like, well, what do I need to do now? I need to get rid of the mercury, right? Get rid of the mercury. Yeah.
Okay, so when the electrons come off of that H going to make the double bond.
Yep.
It's okay to not show anything taking the H?
You can show nothing taking the H. Yep.
Okay, and then also, so would that mercury be, is that?
Still
2
floating around.
Is it 2 plus or is it?
That's again. Don't worry about the oxidation state. It's probably
that's what you said?
yep. Plus 2 plus. Don't worry about the mercury's oxidation state. It's plus charged. We're not gonna ask you to worry about oxidation states yet.
Just doesn't like.
Don't want it bonded to carbon. That's the point. Yeah.
For the last step,
Mm-hmm.
can you have it attacking its own H, the pi bond attack its own H instead of
So
the outside H?
you can, right? So I've shown you where this happens, but not in the presence of strong acid. If H plus is around, this will happen instead, right? Because H plus is a better electrophile than its own H, right? So if H plus is around, you'll do this instead. Good question. Right, the classic. Why are alkynes acidic? Right? It's not just any alkyne, right? It has to be terminal alkynes, right? Only terminal alkynes are acidic. But why is that? Right? So we come back to the same question. So draw a terminal alkyne. And we talk about acidity, right? Say I have Na, NH2 in there. Acidity refers to, right, breaking a bond, or something's acidic if it loses a bond to hydrogen, right? Acid refers to a specific type of electrophile, right? One that has one that loses bond to hydrogen. Now, what hybrid state is this carbon right here? What hybridization state is that carbon? It's sp hybridized. Very good. These electrons that I'm drawing in here, that are bonded to that H, what molecular orbital from this carbon is participating in this bond? and an sp orbital, right? Good. But we know, you guys know, right? Alkyne CH bonds, are they really strong or really weak? Are they reactive or are they strong bonds or weak bonds? They're strong bonds, right? They're short, right? They have really good orbital overlap. But I'm telling you they're acidic. So, for a reaction to take place, one of two things must be true. One of two things or both things. Either the starting material is very reactive, has weaker bonds, or the products are stable. So in this case, right, this is a strong bond, but when a strong base comes along, 1, 2, 3, we can actually deprotonate this, and there's a negative charge there. And why is that? Why will this happen? So where is this negative charge at? This negative charge is where? What kind of orbital? It's in an sp orbital. And an sp orbital, right, is little fat guys. Right? I'm an sp orbital. Right? I'm close to the positive nucleus. I'm happy. Right? Opposites attract. Right? If you can put electron density close to the positively charged nucleus, that makes it more stable. So that's why. That's why alkynes are acidic, because the resulting anion, resulting negatively charged thing, is stabilized because it's in that orbital. If you're an alkene, right, you have an sp2 orbital, which is just that much farther away that it makes that big a difference, and you no longer get that stabilization of the product.
Is it going to be terminal alkene?
Alkenes aren't; those are not acidic.
Oh,
They're not acidic because the sp2 orbital is too far away from the nucleus. So you don't get this, right? You're no longer happy because you're not that close. This is a problem from exam 4.
Hey, don't worry, we just had a field goal block.
2013. It's number 26. Wow, how many problems did we put on this test? 26.
it starts in
Classic. All right. This problem is probably not that important for like the actual exam 4 for tomorrow, but it will be pertinent to the lab practical, so we can go over it. And I'm going to go over a ton, but first thing I would always do with these, right? Basically, I'd ask you. It says, how would you separate these? Not purify, separate these. How would you separate these three compounds? You have an organic solvent, and you can change the pH. Right? So I always like to. What I would do first is, right, I would draw in my lone pairs. So oxygen has 2, nitrogen has 1. Right? I draw these in. And then I would start predicting whether these things were acids or bases, or neutral. Right? So the oxygen, is that going to be an acid, base, or neutral? The phenol here, this alcohol. I would say probably weak acid. Right? What about number 2 here? What's that going to be? It's going to be a base. And what about number 3? It's going to be a base. Which base is weaker? If I letter these A, B, C, the weaker base is why? Why is C a weaker base? When we talk about basicity, what are you talking about?
How reactive the lone pairs?
How reactive, right? We ask ourselves about basicity, right? We're really just asking, will lone pairs react? Right? That's why we thought the oxygen, right? Oxygen is more electronegative, right? So it's going to hold its lone pairs a little tighter than nitrogen does, right? But these two nitrogens, right? This is a lone pair. What molecular orbital? What hybrid state is that nitrogen in? So what orbital is that? Are those lone pairs in? Right, they're in sp3 orbitals. Good. This lone pair over here. What's the hybrid state of that nitrogen? It's sp2. And what molecular orbital are these lone pairs in? They're in a p orbital. And it's actually part of the aromatic ring, right? So if you're in an aromatic ring, you can be very reactive because you're happy, right? The whole point of the aromaticity is that you're less reactive, right? So that lone pair and that molecule is going to certainly be, right, a much weaker base. Right? Because that lone pair is really not reactive. It's part of the pi system, right? So it's going to be less reactive. Good. So if you really want to separate these, right? Let's say you're going to take all of them. What are you going to do first? You're going to dissolve them all in organic solvent.
Yes.
Right? So the whole idea is to get either the molecule either have an overall plus charge, overall minus charge, right? And then once it has a plus or minus, it goes into the aqueous later, right? So which ones can we separate right away? We can do a lot of different things. Let's take, if we take a sep funnel, right? What pH should I make the aqueous layer? Should I make it acidic or basic in the pH? I'll make it basic. So I'm going to say pH equals 12. I'm going to make sure I really deprotonate. So what's going to be in the aqueous layer now? What letter? A, B, or C? A. And where are B and C going to be? B and C are up here, right? This is the organic layer. So now we put organic things go in Erlenmeyer's, aqueous things go in beakers, so A is now in here. How do I get A to come back out of solution? What do I need to do? I need to reprotonate it, right? So I need to make it acidic, and I had to filter it. Now B and C are in this Erlenmeyer. They're going back into the subfunnel. These pictures are good. You should be doing pictures like this. Well, they're not good, but this is the idea.
They're beneficial.
They're beneficial, perhaps. That's the way to put it. Now, but I gotta be careful here, right? So now I gotta be careful about how acidic I make it.
Yeah.
There you go. So, right? So which one's a stronger base than the other, right? More reactive. So do I want to make it really acidic? If I make it really acidic, what will happen? There it is. So let's say I make the pH.
8.
Well, that's not acidic, first of all. but it's 5 or 6. But yikes, 6. Let's say. So if I make it pH 6, what's going to be in the aqueous layer? B. And then C is left over. You separate them. You reprotonate B by making it more basic then again. Filter. And then C, C you rotovap down. You have that isolated, right? Got them all. There you go. Boom. All right, so this is from the Chapter 7 workshop. Right? So it's a retrosynthetic problem. I think it's the last one. So you're given alkyne, 3 question marks, and this aldehyde. Right? And you're asked to figure out a retrosynthetic route and a photosynthesis. So let's work on that now. What is one step back? The tautomerization. So what should we do before we get too far ahead of ourselves? I would number our carbons. Right? And also make a point to realize in the starting material we had how many carbons? 2, and in the product we have 5. So we've added carbons, right? And how many ways do you guys know how to add carbons? 1.
Well, actually,
You have 2 types of reagents, but the mechanism as far as the reaction is concerned, it's the same.
how do you define adding carbons? Because we can add an ester. Like,
Right, so yeah, so I'm talking about making carbon-carbon bonds. How many ways do you know how to make carbon-carbon bonds? Just 1. With 2 different types of reagents. Very good. Alright, so we go 1 step back. So somebody said the enol, so what was an enol? Where would the pi bond be between which 2 carbons?
4 or 5.
Good.
The last two.
That is also correct. Everything is awesome. I should redraw that because we know that, well, you might not know, but, right? So that's like an anti-Markovnikov product, right? Right? The group ends up on the left substituted carbon. So 1, 2, 3, 4, 5. Because addition, I'll tell you in a second why I had to rewrite that. So now we take one more step back. Where do we make enols from? What starting material do enols come from? Alkyne. So where would I add the extra pi bond? Between 4 and 5. Now we gotta be careful how we draw this, right? Somebody's gonna want to do this. Wrong. It's close. Right? It's gotta be like this. That's part of the reason why we numbered our carbons. And a lot of times it's easier just to draw the alkyne first. Draw the alkyne first. Draw the alkyne first. Don't do this. Now we can go, I think we can go all the way back. Right? What do we need to do? So now we know what numbers are these carbons in the starting material. 4 and 5. Right? So in this first step, right, so we always add our carbons last, right? In a retrosynthetic sense, we add the carbon-carbon bonds last, but in the forward sense, we always do that first, right? So here, if I'm drawing, what reagent do I need to use to add this 3-carbon piece? Step 1, I need what? I'll use butyllithium this time, right? It's a negatively charged carbon, right? It's a really strong base.
You can put a slash the other one.
Slash NaH2. Right? Either one works. Right? But you need to have step 1, and then you need to say step 2 is what? How many carbons do we need to add? 3, and they're all in a straight chain, right? So I'd say 1, 2, 3, and I want which bond to form between which 2 carbons? 3 and 4. So what do I need to put on? 4 is going to be a nucleophile or electrophile? 4 is going to be a nucleophile, so 3 needs to be a... How am I going to make 3 an electrophile? Put it on something, attach to something very electronegative, like a bromine.
So you want ones and
Good.
twos not on top of the arrow, below the arrow?
I don't care.
Okay.
You do need to have 1s and 2s. You should have 1s and 2s, right? Because that way you know, right? If it's just below the arrow, someone might mistake that as being a solvent. So 1 and 2.
Can I ask you a quick question?
Yeah.
I've only seen really you do the leaving group be bromine, but it could also be, is that,
It could be chlorine. You guys learn about other leaving groups too. Things that they can come off.
just anything like.
Chlorine, bromine, that's the easiest ones to do.
Okay.
Right. Yep. Okay. So now we're here. Yeah. But now what do I need to do here? I need BH3 OH minus H2O2. And then here, right, this just goes back and forth. Right, that tautomerization, that can just go back and forth. Which one?
Why do we need the H2O2?
So I can tell you that mechanism, but it's very complicated and involves rearrangements. It helps to oxidize.
Just write it.
Yep, write it in there. It's an oxidizing agent. Right, I mean, it's absolutely necessary. Right, it helps get the boron, right? So think of it this way, if you want a simple explanation. right? At one point you have a boron on here, and you need to replace with an oxygen, right? So H2O2 is a very good oxidizing agent. It helps oxidize carbon 5 to allow it to have the OH. It oxidizes carbon 5. Yeah.
How do you know to use a boron and not just H2O?
You need to have BH3 to get the anti-Markovnikov. Right? That's the reagent that. Right, so don't forget that mechanism, right? Don't forget the BH3 mechanism. Otherwise, yep, this is anti-Markovnikov product, right? All right, so don't forget those mechanisms too. So a good point we made here is, right, we made an aldehyde. How many ways do you guys know to make aldehydes? One. Well, ozonolysis can do it, but BH3 on the terminal alkyne is really the best way, the only way to really make it, right? Also, I would say, right, in this case, there is no real other way to do this, but in some of these problems we've done, you can change the steps around, right? There's more than one way to do some of these, right? But again, for this case, right, this is kind of the only way. Good. Right, so if this is number
No, not that one.
17.
Number 19, 19, the bonus, like on the right-hand side. That NA.
Right, so same idea. Okay, same idea. Right, so you can draw this. So it's like 17 has it, and then 19 the bonus. We discussed this kind of thing where, so the different ways you could draw this. You could draw it like this, right, where the electrons, right, 2 electrons on that carbon, and there's like a negative charge, and there's a plus charge sodium. That's more like making it look like an ionic bond. Or, I think sometimes it's easier to see it like this. You just say it's a bond. But you realize it's a really polar bond, where really the carbon has all the electron density. The mechanism doesn't really change, right? If I'm using this to put the final H on, right? I go from here, like that. And if I do it over here, it looks a little different, but it's the same essential idea where I just take the 2 electrons here. I just have to draw them in now. And they go there. So it's the same idea. One's looking at more like a covalent, like it's depicting it as a covalent bond. The other one's depicting it as an ionic bond. Either one's fine. I think sometimes it's easier to see like the sodium. The reason we did it was when, right, and the next step, if we did the next step here, the reason we did it like having like a bond is because in the next step, right, you have your Na dot, and it makes more sense when these 2 electrons come together to then like think of it as like a bond coming, like right, how many electrons are in a bond? 2. So it was just maybe a little easier to see it as like a bond then, even though we know full well it's a really polar covalent bond or even an ionic bond. That's why we kind of depicted it like this year. Either way is fine. I kind of like it this way, personally, but either way is fine.